working group called Proposals for New Searches and Unexplored Signatures. I think it was a very nice workshop for 2 weeks. We had a lot of interesting discussions, a lot of parallel things going on. So I'll present some of the major topics that were discussed. I don't know exactly where all of them will lead to, but for sure there was a lot of interesting topics discussed, and I think some smaller parallel projects that I won't touch here. And basically all the information that I'll show is in the wiki. I've just tried to gather the main things here. I'll try to be very quick so we're not late for lunch. So there were basically 2 plus 1 topics. So this one, it's a more recent addition. So the first 2 ones I've mentioned already at the beginning of the week, Z prime and emerging jets, and then we had some additional discussions on non-standard neutrino interactions. And more recently, I think there was some people discussing about vacuum stability in extra dimensions. Should be, yeah, okay. So I'll briefly go through these 3 just to summarize what has been discussed for those who did not join the discussions. So on the emerging jets scenario, what we had in mind, or what we have in mind, was look on the constraints on Z prime. If this Z prime couples to the dark sector, and the idea is, okay, we have a typical dijet search if Z prime couples to standard model quarks, but if can also couple to these dark quarks. And depending on the dark sector, these dark quarks can hadronize, decay, and then they give a this different signature from the usual dijet search. And the main idea we sort of settled on was, okay, how the constraints on this guy changes as you move from here to here. So we started to look on the available searches, experimental searches. I don't know how easy it is to see them, but here it's usual dijet search presented in the Z prime G coupling mass plane. So this G is the coupling to quarks. And this is slightly different search. This is for this scenario, and it's cross-section versus this displaced vertices guys lifetime. So this dark pions lifetime. So the idea is, okay, how does this move from here to here? Right? Sort of, okay, simple idea. We learned that, okay, we have search. This, of course, we knew this. We learned about the search. We have the results. So basically, it would be a matter of going through the exercise and seeing how these things change. So we took a few steps on that direction. We have a fine rules implementation. I mean, this is a Z prime coupled to quarks or dark quarks, not, I mean, we could basically just use a Z prime model and make some small changes. That was done. And then we sort of have this pipeline working, the fine rules implementation running through MadGraph, and then Pythia. Pythia already has the tools for simulating this dark sector, in the sense that includes dark showering and hadronization. There was also a question about if the Z prime could really be leptophobic, otherwise the constraints from dileptons would probably took over. And we found some papers that claim that this is feasible. You can suppress the couplings to leptons, so we are safe on our assumptions. So in principle, it was more or less, I wouldn't say straightforward exercise, but somewhat simple exercise. And then, of course, we start to dig into these things, and we see that life can be hard sometimes. So concerning the searches that they do, so they have this dedicated search for Z prime decaying to these dark quarks that then hadronize to dark pions, and then they have displaced decays. And we've seen that there are some very strong assumptions on this experimental search. What you'd expect naively is just, okay, I'm looking for displaced vertices. Right? That's the main signature. But they have some hidden assumptions there where some of these guys decay promptly, some of them decay outside the detector. It's not very well justified. And the search strongly relies on a jet plus MET trigger. We don't fully understand how they compute MET. It's very, it's not described in the paper at all. So it's not clear that we can really use these constraints. This might be highly model dependent. So we are still looking into it, something that's ongoing. Another idea was, okay, maybe we can still use the usual dijet searches, even for displaced jets. So, but there was a question there if these dijet searches would still work if these jets actually come from displaced vertices. So Deepak, who was here last week, he took a look into it, discussed with some jet experts, and it seems that even though at least in Atlas, yeah, I think he's in Atlas, the jets are reconstructed without tracks, without the track information. However, they do require, in order to enforce some jet quality criteria, they do require these jets to have a significant fraction of their energy in the tracker. So this probably would kill most of the signal. So the conclusion here is most likely the usual dijet searches would fail to pick up this signal. So these are some of the topics. Then we started to look a little bit in more detail about this dark sector, and we found some references. Most of it was somewhat new to us. So that, okay, it depends a lot on the assumptions you do on this dark sector. If you assume how many dark quarks you assume, if you have two flavors or one flavor, the phenomenology can be quite distinct. So these are still something we need to clear out in more detail in order to understand exactly what are the minimal assumptions. So our idea was to do something fairly minimal and simple, but it's not as straightforward as we first thought. So this is still ongoing. Then we had a separate discussion about non-standard neutrino interactions. I think one of the main ideas was we can have 4 fermion operators like this, which involve neutrinos and leptons, coupled to a quark current or a lepton current. And these are usually highly constrained by data. You can look at these finite states easily, and you typically get strong constraints on these operators. But what are the constraints on this other type of operator, which is a pure neutral neutrino current coupled to a quark current? These are investigated in some papers where they just assume this operator exists. So some of the discussion we had was, okay, can it be constrained by data? What are the constraints? But I think we ended up focusing more on which type of UV model could give you a large operator like this, or an operator with a not too suppressed coefficient, and at the same time suppress these other operators. Right? So how to have this guy large and these 2 operators small. This is not so easy to do, so there was a lot of discussion where we tried to figure out some UV model that would generate this. Some of the things we decided, we saw was at first it's not easy to generate these guys. This is highly non-trivial. You need first you need to start with a dimension 8 effective operator, and then after electroweak symmetry breaking, you generate these guys. Otherwise, there is no way to avoid generating things like this. If this operator is somehow generated by a Z prime, connecting these two currents, then it must be proportional to the breaking scale. Otherwise, by some reasonable conservation of charge arguments, you see that you also generate this operator. Also, it cannot be proportional to neutrino masses, otherwise it's naturally suppressed. So these are some of the topics we discussed, and I think there is no clear idea. There are some proposals. I think Sheng was looking into it, to generate this operator through vector-like quarks and mixing between vector-like quarks and standard model quarks, if this could help in this direction. So at the moment, the conclusion we have is that model building constraints on these guys are fairly strong. It's not an easy thing to achieve, to generate a large operator like this, and at the same time suppress the other ones, and still be consistent with neutrino masses. But I think Sheng and some others will, some of us will keep looking at this. And then I think there was also a parallel discussion about the stability of the electroweak vacuum within the context of extra dimensions. So we know that with the current values of the Higgs and the top mass, the standard model vacuum becomes metastable at high energies. So the running of the Higgs self-coupling goes negative, and so our vacuum becomes metastable. There are some BSM solutions for this. Supersymmetry is one of them. If you include new fields, you also modify the running, and you can avoid the metastability. And I think the idea here is to investigate what happens if you go to an extra dimensional theory. And yeah, and what sort of constraints this metastability or stabilization of the vacuum impose on the extra dimensional theory. So yeah, I received these slides last night, so I don't know if any of you want to add something. No, this is fine. Okay, so just to conclude, Tauhan made a comparison between Pittsburgh and Natal. I cannot do the same. My city, São Paulo, is very, very different from Natal. So I do not look forward to going back home. And so it was very nice. They stay here. I just want to say, since Darren did the same and just remind me, that we do have some master and PhD positions available there. So if you have students, you can send me a message, and we have money for students right now. So thank you.